It's Mr. Kanyile one more time doing your calculus. Right now I want us to move on to the cubic functions or cubic graphs. How do you deal with this section in calculus? It is very easy dealing with cubic graphs. If you've been doing your graphs, the straight line graph, your parabola, your hyperbola, the idea with graphs is the same, and how you interpret them. We'll also interpret these graphs here as well. Number one, there are only 4 important things when you sketch this graph. And in most cases, the questions are asked around those 4 important points. The first one is called, let me just make a rough sketch so that you'll see what I'm talking about. If this is my graph, this is my graph. It's called the cubic function. Remember, these types of graph will be the graphs in the form px cubed. They will be cubed. If I have y is equal to mx plus c, that x is to the power 1, so there is only one x-intercept, or there's only one root. If I have ax squared plus bx plus c, remember it's ax squared. It means I'm going to have 2 roots. So in this particular graph, it will be in the cubic form. Like if you look at this graph here, it's minus 2x cubed. Once it's cubed, then you're going to have 3 roots. But however, it is the same thing as in all other graphs, like in straight line graphs. Like in parabola, for example, if you had a graph like this one, for example, how many roots do you see there? There are 2. It's this one and this one. But if I have, okay, let's make an example. If this is minus 2, if this is 3, before you come to the solution, you would have x plus 2 into x minus 3 equal to 0. Then you come to x is equal to minus 2 or x is equal to 3. That's where it actually comes from. But if what we do, if we've got something like this one, look at this graph. Oops, I wanted to turn here at the x-axis. If this is 2, remember one thing and one thing only. This is the parabola. It has how many roots? It has 2 roots, because it is ax squared plus bx plus c, or in any other form. So this is x is to the power 2. So this tells me that there are 2 roots here. This is the scenario where I have x minus 2 into x minus 2 equal to 0. How do I solve this? I will have x equals to 2 or x equals to 2. These are 2 equal roots. They are 2, but they are the same. It tends at the same position. There are 2 roots there. Unlike this one, there are 2 unequal roots, yet there are 2 equal roots. So whenever we have this scenario, you must know that you've got 2 roots here that are the same. Why am I talking about this? Because I see this fact in this graph. So I know that whenever I have this scenario, I will have 2 roots there. So it's 2 plus 1. In total, there will be 3 roots. So whenever you have, remember this part is called the nature of roots. The nature of roots. So there are actually 2 roots in this particular in this particular graph. That's one part. Let's look at this graph. Let's call this A, B, C, D, E, and F. These are the points that we'll be talking about. When you do cubic graphs, there are only 4 important points. Only 4. And that's what you'll be asked about in your examinations. Those 4. Other questions are there to confuse you. But if you know your basics, then you'll be able to move along. Let's look at these 4 important points. You've been doing graphs from your grade 8 up to now. So this point called the y-intercept. You must know this point. It is the same in all the graphs. Whether I'm dealing with the straight line graph, whether I'm dealing with the parabola, whether I'm dealing with the hyperbola. Right. The y-intercept you find in all these graphs, and you find them the very same way. Remember that along this line we write the values of y. Along this line we write the values of x. So in this line there is no value of y. In this line there is no value of x. So along this line the value of x, we know it is not there, therefore it is 0. So when we talk about the y-intercept, what is to intercept? It is to cut. It's nothing else but the y-cut, the point where the graph will cut the y-axis. That's what the y-intercept is. It is the point where the graph cuts what? The y-axis, the y-axis, the y-axis. That's what the y-intercept is. Remember, these are the x-axis and these are the y-axis. So the y-intercept is this point where the graph intercepts the axis, the y-axis in this particular case. And we know that at this particular point there are no values of x. Values of x are written there. So whenever I'm looking for the y in the coordinates of this point, I know that x is 0 and y will be a particular figure. So at this line, x is 0. At this line, what is x? X is 0. At this line, x is 0. So the y-intercept is the same. So is at this point. The y-intercept there will be also equals to 0. So whenever you are looking for the y-intercept, you make x equal to 0. That's how you find the y-intercept in all the graphs in this world. That's what you do. You make your x, because you don't find values of y here. You only find x's. So there's no x, there's no y on this point. So if I'm looking for the y-intercept, I just make x equals to 0 and solve. It is usually the value we use for it is c. It is usually the constant term if the equation is arranged well. For example, in this one, I can see that this is the constant term. So I can easily tell where this graph will cut the y-axis. So I know the value of this one. It's 20 without even calculating it, but just using my God-given eyes. Right, I want us to that's how you find the y-intercept. I wanted to talk about it. It is easy to find. This is where we should be getting our maximum marks. Number 2, I want us to talk about another intercept called the x-intercept. Number 2, I want us to talk about the x-intercept or x-intercepts. If I'm looking for the x-intercept, what do I make 0? I make y equal to 0, because there is no y there. If I'm looking for the x-intercept, I make y. I've talked about the x-intercept. When I look at this graph, let's look at this graph quickly. If I have this graph, I'm going to talk about the 3 graphs here. Look at this graph, the first one. What type of a graph is this? It's a straight line graph. What is the equation of a straight line graph? There are about 2. Y is equal to mx plus c. The other one will be y is equals to mx plus c. The other one will be y minus y1 is equals to m into x minus x1. Right, I want to talk about this x. If you look at that x is to the power 1. It means that I'm going to have one x-intercept. This is the only x-intercept. This is the only point where this graph cuts the x-axis. It's called the x-intercept. I'm talking about the straight line graph. I'm trying to move towards the cubic function that we're doing today. If you look at this graph, let's have another graph here. Let's have another graph. Let's look at this graph. What type of a graph is that? It's the parabola. What is the general equation of the parabola? It is y is equals to ax squared plus bx plus c. What is the other equation? It is y is equals to a into x minus p all squared plus q. What is the other one? It is y is equals to a into x minus x1 into x minus x2. This is the equation of the parabola. I'm not interested in these graphs. That's what we're doing, but it's important that we pass in here. Remember, this is to the power 2. This is what I'm interested in. This is to the power 2. This x is squared, so it's to the power 2. This times this, it will be to the power 2. So I'm trying to emphasize that if you've got x squared, you are going to have 2 roots. 1, 2. If you look at this one, how many roots do we have there? We've got 1, x cut. So we've got 3 roots. You might find roots like this one. Don't forget that. We might even find roots like this one. There will be 3. Remember that here there will be 2 equal roots plus the 3rd one. So it is important that when we talk about the x-intercept, you let y be equal to 0. You don't stop there with the x-intercept. After that, you factorize. You find the value of x through factorization. There are so many methods of factorizing. At times you'll have to use the synthetic method, which I will show you, or you use the long division. Others, they just use their calculators. Right, that was point number 2, the x-intercept. If you can find the x-intercept, the better. But we're dealing with calculus. The 3rd part that I want us to look at will bring us to calculus. That's why we study these graphs in calculus. We said this. We've talked about this one. We've talked about this one, which is the y-intercept. You make x equal to 0. We talked about these ones, which are the x-intercept, and we know how to find them. We let y equal to 0. Then you factorize after that. Until you find these values of x, you are expected to find the 3 values of x in this particular case. That's number 2. What is number 3 then? This is what I say, it is the gist of studying these graphs. We call them stationary points. Others, they call this local minimum and local maximum point. Local minimum and local maximum point. Others, they simply say it's the turning points. There's nothing wrong with that. Now, the 2 turning points, we call them stationary points or the turning point. Right, this graph goes up, becomes stationary there, it goes down, becomes stationary there and it goes up. It turns, in other words, at that particular point. Remember, we're dealing with calculus. What is calculus? It is the study of gradient. We're just studying gradient in this particular section. Now, I can see the gradient here at this point. But once the graph reaches this position, position B, there is no gradient. It becomes stationary. There is no gradient here and there is no gradient here. What is a gradient? It's a slope. You can find a slope here, you can find a slope there, you can find a gradient there. But at point B and point C, that's are the points that we refer to them as stationary points. So stationary points are point B and point F in this particular case. Now, what brings this to calculus? Calculus is the study of gradient, and we know something about the gradient at this point. What is the gradient here? It is 0. What is the gradient? It is the derivative. So when we're looking for this point, you let your dy dx be equal to 0. I'm letting my gradient to be 0 because I know that at this point there is no gradient. So if I'm given a particular graph and I'm looking for these points, I have to differentiate the graph that I'm given and make it equal to 0 because I definitely know that at this point there is no gradient, and you're going to get 2 values of x. One x will belong to this side and the other x will belong to this side. When looking for the corresponding y value, you'll take the x that you found here and substitute it in the original equation. In the very same way, to find the corresponding y value of this one, you'll do the same thing. Take the value of x that you found here and you'll substitute. If you found x, you'll have to go back and substitute it in the original equation to find the corresponding y value. That becomes very important when dealing with this graph. We're studying gradient. So we know that the gradient at this point is 0. That gives us a plus. It makes us easy to find these particular points. We just let the derivative or the gradient be equals to 0 to find the x value. And to find the corresponding y value, you take that x value, you substitute it in the original equation. Now I want us to move on to the 4th point. We started with the y-intercept. It is very easy to find the y-intercept. We simply make x equal to 0. We talk about the roots, the x-intercept. How do we find the x-intercept? We make y equal to 0, then we factorize. We'll talk about the other ways of factorizing. Others, they will use long division. Others will use synthetic method. Others will simply use their calculators. the x-intercept, I think they're also important. They've got more marks also. Then the stationary point, our gist, the two turning points. Remember, this graph is made out of this turning point, which is concave down, and this one, which is concave up. We call this local maximum. It's the maximum value there. It's the local minimum, because the graph cannot be found lower than this one. This point is the local minimum. That one is the local maximum. At times we'll call them like that, or the two turning points, or the stationary points, or it is advisable that when you calculate these points, especially the two turning points, put them there. Put those coordinates in your particular graph. The question, when you do this, you attack this in the examination, you can be asked in two ways. Number one, you might be given a graph, like in this example that I'm giving you, that we'll be doing with you, and be asked questions. Or you might be given questions and you end up sketching the graph. So you must know both. You must know how to sketch the graph, and you must know how to respond to questions when you're given graphs. Right, we let your derivative be equal to 0 when looking for the stationary points. In this case, it is B and F. What are the stationary points in this particular case? In this graph, it is T and A. And there's something that we know here. We know that there are two roots here. If I'm looking for the coordinates of this point, I know that there's no y here, so already the value of y will be 0 in that particular point. Right, we're talking about the stationary points, the two turning points, the gist of the cubic function. The last point is called the point of inflection. This is another point which is important when we're dealing with cubic graphs. It's called the point of inflection. Remember, we're studying calculus. At this point, we set the gradient. There is no gradient here. It turns, the graph comes here and turns. Remember, if you look at this and you think of the background, I think you must be able to see the two parabolas, one facing down and the other one facing down, facing up. I'm saying you must be able to see that this is made out of a parabola that is facing down and another one that is facing up. This one is facing down, it's a parabola. This one is facing up. Now what is happening here? This graph went up, it turns. How do you find this point? We look for the first derivative. Comes here, it's supposed to go down if it was a parabola. It was supposed to go down this way. This one was supposed to go up that way, right? But it didn't. What did it do? It turned again. It goes up, it turns, we find the derivative. It goes down and turn again, so we find the second derivative in that particular point. Now, so a point of inflection is the concavity of the two graphs, one facing up and one facing down. Where this starts to turn instead of going up, that point is called the point of inflection. So when I look at this, I know that the point of inflection might be somewhere here in this region. We can be able to calculate it specifically. What is the value of that one? How do you calculate the point of inflection? You find the second derivative, f of x 2 prime. You differentiate the first part, then you differentiate again, and you're going to let your derivative, the second derivative, be equal to 0. You let dy second derivative be equal to 0. Then you will be able to find x. If I'm looking, okay, that's how you'll find x. To find the corresponding y value, that's how you'll find x. How then will I find y of the point of inflection? To find y of the point of inflection, remember you've already found your x through the second derivative. To find y, you go to the original equation. For example, this equation, you put these values of the value of x there, then the value of y will come from that original equation. You substitute the value of x of your point of inflection to the original equation to find the corresponding y value. Right, these are the main 4 points. The questions will only be revolving around these 4 points. Do I understand what a y-intercept is? Do I understand how many y-intercept do I expect? I expect only one. Do I understand what the roots are? The x-intercepts. I expect about 3 x-intercepts. At times I might have 2 of them together. where it is a turning point. I might expect 2 of them together. So generally I'm expecting 3 x-intercepts. At times I might sketch graphs that does not even touch the x-intercept. We'll make examples of those. Maybe it touches once and 10 on the air there. The next point that I want to talk about is the stationary points. These points are important. They bring us to calculus. Stationary point, the derivative at the stationary points, the gradient at this point is 0. So whenever I'm looking for the stationary points, I let my derivative be equal to 0. Then the last point that we talked about, that's how you find the x of the stationary point. You let your dy dx be equals to 0 there, you'll find two points. That's how you'll find the x of the stationary point. To find y, you take that x, you substitute it in the original equation. Let me show you another way. The easiest way to find the x of the turning point. This is what you do. Remember that there are 2 coordinates here. There is, let me call this x1 and y1. There are also coordinates here, x2 and y2. How do you find the point of inflection in another way, apart from finding the second derivative? This is what you must do. Watch here. You take this x, which is x1, you add it to this x, which is x2, which is x2, then you divide it by 2. This is how you find the x of the point of inflection. Take this x here, you add to this x, then you divide by 2. That's how you find the point of inflection. Or alternatively, point of inflection, you find the second derivative of this graph. Not the first, but the second, you make it equal to 0. You'll come back to the same solution as well. So you're spoiled with choice. So that's basically about functions. The next thing that we might ask you is to move it up and down. You must know that when I move it up, what happens? This value will move up as well. The whole graph will actually move up. This value will also move up. The y value will also move up. The x will be the same. If I'm moving it along this way, I must know also what's happening there. Let's get into these questions and try to respond to them. Thank you. I want us to see how we set these questions in the exams. Practice more questions, especially from 2021 to 2012. Practice more of those papers because they will sharpen you for your final examination. If you look at this one, I've taken it from November 2008. I've given you an option where I sketch the graph and ask questions on the sketch graph. At times, it might be the questions I will end up sketching the graph. So you must know both. I think we never touch on this one. Look at this graph here. Look at this graph. This is the graph. This is the Cartesian plane, and this is the graph. Look at this one as well. And this is the graph. If we're dealing with a parabola, I might have a graph like this one or a graph like this one. If the graph is facing up, we say our A is positive. It is positive. This graph is positive. This one is negative. So it will have a negative sign at the beginning. It's the very same thing here. This graph here is positive. This one is negative. It will have a negative value at the beginning. For example, when I look at this graph, it is the same as this one. It is negative. Therefore, that's why it is negative there. If it is negative, I know that the shape will look like this one. If it is positive, it will be the other way around. So it must be able to see when the graph is positive and when it is negative. So you can see that this one is the same as that one, hence negative. Right, that's one part. Remember, we said there are 4 important things when you're dealing with cubic functions. Number 1 is the y-intercept. Number 2 are the roots of the x-intercept. Number 3 is the 2 turning points or the point of inflection or the local the stationary points, local maximum, local minimum. Lastly, it will be the stationary point where your second derivative is equal to 0. Right, let's look at this one. Before I even do anything, when I look at it, I know where that value belongs. I exactly know where that one belongs. It belongs in y-intercept C. I know that this is 20. I can simply put it there. I know it's 20. Okay. I said think along the 4 points. Number 1 is the y-intercept. That's why I'm putting it there. Number 2, the x-intercept. Number 3, the turning points. And number 4 is the point of inflection. I've seen the y-intercept. I've discussed it, I've talked about it, and I've put the value there. So the next question that comes to my mind will be the x-intercept or the roots. But when I look at the diagram, I've got this root and these 2 equal roots. So I know that I have that at the back of my mind, that I'm going to have 2 roots here. Right? That becomes very important. I'm going to have 2 roots here and 1 root that side. But the way that they've given me, they made my life easier. They even went further and factorized this for me. Now, what is this saying to me? If I have something like this, let me just put it this side. If I have 2x minus 5, let me just put it as it is so that we'll understand where everything comes from. Into x plus 2. What does this squared mean? It simply means another x plus 2. That's what it means. That's what it actually means. So we've got 2 equal roots this side. Right? Let me just leave it as squared. I know, young boys and girls, that if I'm looking for the x-intercepts, what must be 0? Y must be equal to 0. At the moment I'm given g of x, which is my y, I've got to make this equal to 0. So if I make this 0, I can take this whole thing, go that side and be positive, and I'll have 0. So I'll have 2x minus 5 into x plus 2, x plus 2 equal to 0. Because when I'm looking for the x-intercept, I make my y equal to 0. Right. Let's do it this way now. I know that the next question will be asking for the x-intercept, maybe. Now, where are my x-intercept? This part is the x-intercept, that part is the x-intercept. Let's look at the question now. Calculate the length of AB. Why are they not asking me about the x-intercept? Yes, they are asking me about the x-intercept, but in disguised. Because you're not going to know the length of AB if you don't know that value and you don't know this value. So they've asked us about the x-intercept in disguised. Let's do that. Where am I going to find the solution? I'm going to find it where they've already solved it for me. It's going to be very easy. Let's do it here. What is x here? So take x will be equals to, take 5 that side, it will be 5 over 2. Right? We divided by this 2 on both sides. What is 5 over 2? It is the same as 2 into 5, 2, 4. It's 2 and 1 over 2, 2.5. Yes, it is 2.5. Or this side, x is equals to minus 2. Remember this side, it is where it is a turning point because it is squared there. Remember it was squared. I did not put the squared there. Because it was squared there, hence I know where x is equal to 2, it is where it will be turning because there will be 2 equal roots at that particular point. And I know that value is what? It is negative. When I look at my graph, this part is negative, that part is positive. Hence the positive root will go this side and the negative root will go this side. And I can tell that it will be a turning point because of that square. Now I know exactly the value of this point, therefore. It will be minus 2. What will be the value of this point then? It will be 2.5 or 5 over 2. Now, we were not asked for roots, but we had to find roots for us to respond to this question. So whatever questions that they ask us revolves around this 4. Even though they might not ask us to calculate the roots directly, but we will need to find them. Right, the length of AB. Remember the distance, there is no negative distance. I can't say that this distance is minus 2. The distance is always positive, it is 2. From here to town, if it is 5 kilometers, even when I come back, I will not say, now that I'm going back, it is minus 10 kilometers. It will still be the same thing. So the distance is always positive. Once they talk of the length, remember they're talking about the distance, the length, and the length is positive. Now watch here. So the distance from here to here is what? It's 5 over 2. What is 5 over 2? It is 2.5. So the distance from here to here, it's 2.5. How did I find that? I use my roots, my x-intercepts. What is the distance from here to here? The distance is 2. But the value of x there is minus 2. But therefore, what is this whole distance? It is this 2 plus 2.5. What is 2 plus 2.5? It is 4.5. No, so when they, okay, you'll work it out. Number one, we'll set g of x is equals to minus into 2x minus 5 into x plus 2 all squared. I know this part will give me a turning point. Because I'm looking for roots, I'm gonna let g of x be equal to 0. Make this 0. If this is 0, this whole thing will come this side. I will have a positive 1 now, which is 2x minus 5 into x plus 2 all squared equal to 0 in this particular way. Therefore, my x will be equals to 5 over 2, or x will be equals to minus 2. I know where to put this one back there, and I know where to put that one back there. Therefore, the length of AB, distance AB, will be equals to this distance, which is 2 units, plus this other distance, which is 2.5 or 5 over 2. Therefore, the actual length, there is equal sign there. Therefore, the actual length of AB will be 2 plus 2.5, which is 4.5. Others which is 4.5. Others can write what? What is 4 times 2? It's 8 plus 1. Others might have an answer of 9 over 2 units. Remember, it's the distance. If you're not given whether it's centimeters or meters, you leave it as units. So the distance from here to here, it's 4.5 units. Don't forget to write those units. That's how we sometimes ask you for the x-intercept. We might just ask you the question. Remember one thing only, the distance is always positive. Look at the second question. I go to the exam room with 4 questions to respond to. Number 1, y-intercept. Number 2, x-intercept, which we've already responded to. Number 3, it's the stationary points or the turning point. Number 4 is the point of inflection. We've already dealt with these 2. So at the back of my mind, I still have the point of the stationary points. I still have the point of inflection. Let's do this thing. This question is asking for the x-coordinate of t. What is t? T is the stationary point. T is the turning point. But I know that when we deal with cubic functions, we usually have 2 turning points, 2 stationary points. Local maximum and local minimum. So they're asking for the local maximum, which is point T. Why are they not asking about the coordinates of this one? Because this is a turning point, that is a turning point. Because we've already found this one while we were doing the x-intercept. It will be foolish for us to ask you both of them, because you already know this one when you calculated it there. That's why, therefore, they're just asking for the x-coordinate of t. Are they asking for both coordinates? No, they just want so huge marks. These are big marks. These are giveaway marks. Make sure that you grab these marks. All right. I know at the back of my mind, I'm just looking for t. Remember, I'm dealing with calculus. What is calculus? It is the side of gradient. Do I know the gradient at this particular point? Do I know the gradient at point T? Yes, I know the gradient. It is 0. What is the gradient? It is the derivative. So if I differentiate what I'm given here, at this point, the derivative will be equal to 0. And I know that I'm going to get 2 solutions. One will be for the local maximum, the other one will be for a local minimum. And I know this value must be 2. Even if I'm doing this question, I will get both of them. And if I don't get minus 2, and I will know that I'm wrong. Let's do this thing. Calculate the x-coordinate of t. At t stationary point, this one and this one. But I'm only asked for t. I just do what I know. Remember, whatever questions that they ask me, it revolves around this 4. I repeat, x-intercept, y-intercept. Remember, there might be 3 x-intercept, y-intercept, stationary points. I must know how to find stationary points. I must know how to find the x-intercept. Number 4, it will be the point of inflection. Now this part is pushing me to thinking about number 3, which is the stationary points. The x-coordinate of t, and t is at the stationary point where the derivative is 0, where there is no gradient, derivative gradient. Let's do this thing. We let g of x prime be equal to 0. Why are we doing this now? At this point, there is no gradient. There is a gradient here. How is this gradient? It is positive. How is this one? It is negative. How is this one? It is negative. How is this one? There is no slope there. There is no gradient. Hence, the gradient at these 2 points, it is 0. And I know I don't know the value of x there. I'm looking for it, but I know the value of x here. It is minus 2. So as I calculate this point here, I'll be getting 2 points, and I must get this minus 2 for it to work. Let's do this thing. Let's find the derivative there and make it 0. This times this, it's minus 6x squared. That's the first one I got. Oh, yes, let's multiply this one. It's also 6x. It's minus 6x. Let's differentiate this. It is plus 12. Remember your rules. You also differentiate this one. Derivative of a constant, it is 0. We let this derivative, this is my average gradient, we let it be equals to 0. Because at this point, there's no gradient. That's what we're saying here. And whatever we write, it should have a meaning to me. Because I'm dealing with calculus, which is the study of gradient. And we are saying the gradient here is 0. This is what I'm saying. The derivative, it is 0. So when I differentiate, for this point, I won't find the gradient. The gradient will be equals to 0. Let's move on. Remember that this is going to give me 2 values of x. It becomes a simple algebra, grade 9, factorization. I've got 3 terms. This is just a trinomial from your grade 8, grade 9. Now you must be, these are giveaway marks. Make sure that you don't lose these marks. What must we do? Once we're at this stage, we must factorize. What is the first thing we do when we factorize? Is to look for a common factor. Don't just calculate it. Don't pray about it, just look for it. I can see that there's a common factor here of 6. Because at the end, I want to make the coefficient of x squared positive. I would rather divide by -6, -6, -6, -6. Right, let's do that. If I divide this by -6, I will have x squared. If I divide this by -6, negative and negative, I will have positive x. Right? If I divide this by -6, I will have negative, what do I have here? -2. Then this will be equal to 0. So your factorization is important. Divide everything by 6, make sure that you get it correct. There are so many mistakes that we might make here. But let's move on. Now that we've got our trinomial, we can factorize because there is no common factor anymore. What are the factors of x squared? It is x and x. Right? Now we're looking for factors of 2 that will give us 1. That is 2 and 1. Because this one is positive, the bigger number between these 2 must be positive, the smaller number must be negative. So that when we say positive 2 times -1, we're going to get that one. When we add these 2, we're going to get that one that is there. That's how you factorize. Right, we're going to our solution now. Remember one thing. We're looking for the x value of t, but you can't just find t alone. We're going to find t and a, because these are the 2 turning points. But I already know what answer must I get to this side. I must get 2. If I don't get 2, then the whole thing is wrong. Let's work it out. Solve for x here. So x will be equals to -2. I got this -2. Then I'm okay. Or x is equals to 1. Okay. How is my x here? It is 1. Wow, how is my x here? It is -2. Did I expect to get -2 here? Because it is there. Look at the x's this side. They are positive. and I'm getting a positive answer. So I laugh all the way to the bank to collect my marks. But remember, we're not looking for both of these values. We were not looking for the x coordinate of A and T. We're just looking for the x coordinate of T. I respond to the question, therefore, the x coordinate of T is equals to 1. This is where I respond to my question. What is this saying to me? The value of x here is 1. This is what it's telling me, right? That's how you go about doing solving for this. In other words, the question was asking for us about, do we know how to calculate the stationary points, the two turning points, the local maximum and the local minimum point. Remember that at this point there is no gradient. Let's look at 9.3 now. Determine the equation of the tangent to G at P 3 x is minus 3 and y is 11 in the form y is equal to something, right? Let's look at that, and they specific how they want it. Determine the equation of a tangent. Do we know what we're looking for? We are looking for the whole equation, the equation of the tangent. Do I know what is a tangent? Yes, a tangent is a straight line. Y is equals to mx plus c. So what are we looking for? We're looking for m and c, the y-intercept and the gradient. That's why we're doing this, because there's a gradient. And calculus is nothing else but the study of gradient. Determine the equation of the tangent to G. This is my G at point P. Oh, I want us to put this in perspective. Determine the equation of the tangent to G at this point. This is where point P. So in other words, we're looking for the equation of a tangent at this point. This is the equation of the line that we're looking for. But we know that this one is a tangent here at P. We're not looking for the equation of this one, but we're looking for the equation of this tangent. But this tangent is related to this graph. How related are they? At this particular point, this graph of a tangent is the same as the cubic graph. Do I know the value of x here? Yes, I know the value of x here. I'm given it is minus 3, and I know the value of y here. It is 11. Those are the things that I know at point P. Now, the question says, determine the equation of a tangent. We're looking for the equation of this line. Is this gradient positive or negative? This gradient here, it is negative. So I know that I'm going to get an m that is negative. I know that I'm going to get this gradient must be negative. Look at C. What is C? C is nothing else but the y-intercept. Now, if I'm sketching this line, the y-intercept will be somewhere here. So my y-intercept will also be negative, and it should be a slightly bigger value, my y-intercept. So I know exactly what I'm looking for. I'm looking for the equation of this line, and this line is related to this one because it is a tangent to it. So the gradient at this point for the tangent is the same as the gradient for the cubic function at that particular point. Now, if I can find the gradient of the cubic function at this point, it will be the same as the gradient of the tangent at this particular point. I think that's the key, because when the two graphs meet, they are the same. And the point of intersection in this particular case makes this line to be a tangent. And that's exactly what we're looking for, the equation of a tangent, where this graph touches the cubic graph. But I know that when I'm looking for the tangent, I'm just looking for two things. M, the gradient, or the derivative, and C. But I can't find m of this graph. But I can find m of this graph at this point, which is the same as the gradient of this one. That's what we're doing here. I repeat, the gradient of this line is the same as the gradient of this one at this particular point, at the point of contact. So if I'm looking for the gradient of the tangent, I've got to look for the gradient of this one at this particular point. Let's do the same. Let me find my gradient, g of x prime, my average gradient in this particular case. It will be equals to, I think we've done it somewhere, I don't see it, but let's do it again. It will give us what? Minus 6, is it minus 6? Minus 6x squared. Let's move on. Another minus 6x. It must be somewhere here. Plus 12. 20 will be 0. This is the gradient. This is the average gradient. But we're not looking for the gradient anywhere. We're looking for the gradient at this particular point. What is the value of x here? In this particular case, y was not that important. It was x. So don't be confused and choose the wrong one. Because I'm looking for the gradient where x is what? Where x is minus 3. Where x is minus 3. If you look at this one and this one, where there was x, we push in minus 3. We do the same thing here. Where there is x, we're going to push in minus 3. This will be minus 6 into minus 3 all squared, minus 6 into minus 3 plus 12. Let's quickly calculate this. 6, oh, minus 6. Oh, brackets. If you calculate that one, it will come to minus 24. So the gradient at this point of the cubic function is the same as the gradient of the tangent, which will give us minus 24 if you use a calculator. The question says, determine the equation of the tangent. What is it that we find thus far is the gradient. We know that the gradient there is negative 24. Look at the line. Remember one thing and one thing only. If I have a line like this, how is this gradient? This gradient is positive. How is this gradient? This gradient is negative. If you forget, like me, look at these x's. How are these x's this side? They are positive. How are these x's this side? They are negative. So if my line comes from this side, the positive side, the gradient will be positive. Gradient is positive. If it comes from this side, the gradient is negative. 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 Hence, I'm getting a negative gradient there. Once we have the gradient, we need to find the value of c. Remember, okay, we now have a gradient of the tangent. Is there anything that we know about this tangent? There is a point that you know, a point P. It is on this line. You use the point that is on the line. So I can use my M. This is my M. And I'm going to use point P. What are the coordinates of point P? It is minus 3 is 2, 11. I'm going to use these two to find the equation. You can use y is equal to mx plus c if you like, it's fine. You can use y minus, you can use this one, which is y minus y1 is equal to m into x minus x1. Or you can just use this one. It will all give you the same thing. This is x1, this is y1. Let's push it in here. So y minus, what is y1? It is 11 is equal to, what is my m? My m was gradient of the tangent was minus 24 into x minus. What is x1? x1 in this particular case is minus 3. So this minus and this minus will give us plus 3. That's what we have. Let's work it out. This will be y is equals to, you take this, you multiply by that, it will be minus 24x. You take this, you multiply it by 3, 24 times 3, 72. We said this times this, it's minus 24x. This times this, it's minus 72. Take this 11 this side, it will be plus 11, right? Therefore, the equation of the tangent will be y is equals to minus 24x 1 and 1, 1, this 6 and 1, it will be 6, 7 and 1, it will be 6, so it will be minus 61. This is the equation of a tangent. This is what we're looking for. Remember, when you're looking for the equation of a straight line, you're just looking for M and C, and we found both. So the equation of a tangent is y is equal to minus 24x plus 61. I want us to look at the next question that I want us to look at here. Now, do we know this, the x-coordinate here? We know the x-coordinate here. What did we find as x here? We found it as 1. We don't know the y-coordinate, right? It's fine. We find the x-coordinate to be 2 and y is 0 there. The next question that I want us to look at is the point of inflection. Remember, the point of inflection is the concavity of the two graphs. It's where we look for the second derivative. I want us to calculate the point of inflection here. Right? I want us to look at the point of inflection in this particular one. Do we know the first derivative? Yes, we do know g of x prime. We've been calculating it all along. It is here. It is minus 6x squared minus 6x plus 12. But at the point of inflection, the second derivative is 0. Now, g of 2 prime will be equal. I'm differentiating for the second time now. This was the first time, I'm doing it for the second time. It is equal to what? This times this, it is minus 12x minus 6 and 0. This is what we have. Remember, I'm looking for the point of inflection. If I'm looking for the point of inflection, I let my g of 2 prime x equal to 0. So I make this equal to 0. Hence, this will be minus 12x minus 6 equal to 0. My second derivative is equal to 0. Take 12x this side, it will be positive, and 6 will remain negative here. So then I will have 12x equals 2. I took this one that side, I kept that this side. Right? Let's work it out. Let's work it out first. We set this one this side, it will be positive. This one will remain negative. It's fine. Then we divide by 12 on both sides. Therefore, x will then be equals to, this is negative, 6 there goes once, 6 here goes 2. This is the point of inflection. It is somewhere on the negative side. Yeah. This is the value of x that they are talking about there. It is what? It is minus 1 over 2. That's what the point of inflection is. But if we were looking for both coordinates, both x and y, we're going to take this value here and substitute it here to find the corresponding y value of the point of inflection. Let me show you another way of calculating the same point of inflection. Alternative method. I said to you, if I'm looking for the point of inflection, I'm going to take the x of the stationary point, add it to the other x, divide by 2. I'm saying to you, if I'm looking for the point of inflection, which you've already calculated there as minus half. Let's see if the other method is correct. What is the first x there at t? X there is 1. Okay, x is 1. I said x1 plus x2 of the turning points over 2. We find the average of the axis of the turning point. Therefore, x is equal to, what is the first x there? I see minus 2. This one, it is minus 2 plus, what is the other x? It is 1. x1 plus x2, we divide this by what? By 2. Therefore, x of the point of inflection minus 2 plus 1, it is minus 1 over 2. It is exactly the same thing as that one. Your spoiled with choice. You can use whatever method that suits you. I said you can let your derivative be equal to 0 for the point of inflection, or you add the two values of x here and divide it by 2. You'll find the very same point, which is called the point of inflection. Thank you. Okay, let's go on with our function, cubic graph. The last part of this graph is to interpret them, to see what happens if you move them up or down or sideways. Remember, if they are moved sideways, those that are put in brackets, that will be the movement. But let's look at this question. It was 9.4 in November 2008, question 9. Determine the value or values. We don't want to be specific whether it is one value or many values. Why? If you do your examinations and the question says find the value, it becomes easy. It simply means that k is equal to something. So it gives you direction that if it says value, you're going to have one value. But if it says values, it might be the inequality sign, where k is greater or k is less than. So when we say value or values, we don't want to be specific whether you use equal sign or inequality sign. That's why we use both value or values. Once it says value, k is equal to something. Once it says values only, it will be an inequality sign. But here we don't want you to be sure whether it's this sign or this sign, one value or many values. That's why we put it in that form. So that becomes important. You must be able to understand that first. Determine the value or values of k for which this one has, what is this one? This, I can see that this one is this one, which is this graph, okay? For which this graph equals to k has three distinct roots. What are distinct roots? Number one, what are roots? Roots are the x-intercepts. For this graph, we've got 1, 2, 3 x-intercepts. But these x-intercepts are not distinct. They're not on its own, because here there are two equal roots on the same position, so they are not distinct. At this moment, they are not distinct. Distinct roots will be roots like this one. This one is on its own, this one is on its own, this one is on its own. These are three distinct roots. At this moment, they are not distinct because there are two here. They're not all on its own. The question says, determine the value or values of k for which this graph has three distinct roots. In other words, we need to move it up or down. But if I look at this graph, at this moment, there are two here and one there. Suppose the question says, determine the value or values of k for which this graph will have one real root. If the question wanted to find the situation where this graph will have one real root, it means that we would have shifted it up so that it will only touch on this part. If you shift it up, it will be above this value here, which we don't know. I think we need to calculate that value as well. Let's quickly work on this value. I think we will need it. If x is 1, what is the corresponding y value? How do you find the value of y here? You take this x, you substitute it in the original equation. Let's quickly do that. If I push 1 here, I will have -2. If I push another 1 here, +1, I will have another -3. Push 1 here. All right, I'll be left with 7 plus 20. So this will be 27. So the value of y there is 27. So if I wanted this to have one real root, I'll need to push this above 27 in that way. Now, but the question says, determine the value or values of k for which this graph will have three distinct roots. People use different methods. Remember that. Okay. At this moment, okay, let's use the simpler one. Let me just take it up. If I draw it here, how many roots am I touching? 1. Do we see that? I'm only touching one root. We want the situation where this will have 3 roots. In other words, I'm moving my x-axis. If I move it here, it will have, still they are not distinct because there are 2 there and 1 here. If I do it here, 1, 2, 3. Now this is part of my solution because we want to have 3 distinct roots. If I do it here, 1, 2, 3, they are still 3 distinct. Here, 1, 2, 3. If I do it here, not distinct. If I do it here, 1 root. So for this to have three distinct roots. The solution is between these two. Are we together? So k can be any value in between here. So the solution for this one is very simple. We are going to say k is between, let me just look at it again. K is above 0 but less than 27. K is greater than 0 but less than 27. I think this is how I will go about this. So it should be above 0, but yes, it should be k is above 0 but less than 27, because this is where the solution will be. That's how I'll go about doing this one. Thank you.